Okay, let's see. I should be live, hopefully. Okay, I still have to understand how these things work. Okay, well, welcome to another live, if there is anybody watching. Uh, I am thinking of changing the format a little bit for next time. For today, I think we're gonna do exactly what we did the last two times. But, oh, wait a second. Okay, do I do this? Okay, so hi Tobias. I was thinking for next time to do something, to start doing something that probably is a little bit more interactive in the sense of maybe looking at open problems so that I'm trying to think of things that are better even for people to watch afterwards when the thing is done. And so maybe talking about going through and organizing the list of open problem might be a better thing to do during the live. But at the end of the day, I don't know. So for today, hello WWKK. So for today, I think we are just going to, let me see, I have to share the thing, to try to close the discussions that we had the other time about problems with infinite dimensional spaces and write down all the things that need to be written down so that then I can take it off of my mind and start thinking about everything. Another option that I was thinking might be probably better for me is to talk about things that I'm actually doing during the week. So originally I thought I'll do the live so that I force myself to do the things that I'm not doing. But then I think that I come here and then I don't have enough clear enough ideas of what I need to do, and so I think it just becomes boring and a bit of a mess. So anyway, so today I did write some things down that we can go over, and then you guys tell me whether they make sense or not. So let me start by doing this. There we go. And let's see if any of this makes sense. Okay, so I can probably. Oh, can I do do I have it set up like this? Let's see. And now I can probably do this. Is this a better ratio for the screen? Let's see. There is such a delay even, but okay. Well, let's pretend it's okay. Okay, so let's go through it. And so there is the part that in principle we already seen last time, but I think it's better to go through it and then let's write the new part. Okay, so in the previous section, so we pretend that we have done the whole section before, and we just go through the problems that there are in infinite dimensional spaces. So we say in the previous section, we restrict ourselves to finite dimensional spaces. In these spaces, all measurement can be understood as having finitely many outcomes, and all those outcomes can be understood as quantum states. In this section, we will extend the discussion to the infinite case and see the extension is problematic. Infinite dimensional spaces, in fact, seem to hide the source of the infinity and require the existence of states that cannot be thought as being physically meaningful. The exact mathematical representation of these cases then is still an open problem. And there are two potential sources of infinity in physics, the infinitely large and the infinitely small. The infinitely large comes from unbounded quantities, for example, the number of particles in a gas or the distance of a particle from the origin of the reference systems can be in principle arbitrarily large. In this case, infinity is just the range of possible values and not a value itself. It would not make sense, for example, to say that a gas has infinitely many particles or that a particle is infinitely distant infinitely. Am I spelling these things right? Probably not. Whatever. I never, I don't think that the E is there. Okay, no, it is there because otherwise I get an error. So I don't know why it's underlined here. Infinite distance for the origin, unless we are talking about the limit of a process that takes an infinite amount of time, not the infinitely large. It does not change the nature of the quantity. The number of particles is a discrete quantity and the position is a continuous quantity regardless of whether we're allowing an infinite range or not. And I have to remember to look at the chat because otherwise I don't see it. And thank you, WWK. I don't know if my efforts are inspiring, but I think there are things that need to be done. Okay, so the infinitely small comes from the ability to refine measurements indefinitely. So this is a different sort of infinity. It's the infinitesimal. For example, we assume we can measure the position of a particle with arbitrary position. While the infinite precision measurement is never realizable, the infinite precision value can be understood as the information needed to specify the finite precision outcome at all levels of precision. That is, if we knew the position with infinite precision, we would know all the possible finite precision intervals in which the particles can be. The infinitely small then changes the nature of the quantity from discrete to continuous. Over a finite range, a discrete quantity will have finitely many possible values, while a continuous quantity will have infinitely many. We can characterize the difference in the following way. A measurement will tell us whether a particle value is within a set of possible values. If the quantity is continuous, all measurements will always restrict the range of possible values to an infinite set. That is, any measurement of position will have a finite uncertainty, which will include infinitely many possible positions. If the quantity is discrete, at some point we will have a measurement that identifies each possible case, I guess. That is, we can count exactly the number of particles, which restrict the measurement to only one possible case. Intuitively, the range is infinite in either case if it cannot be always covered with finitely many measurements. That is, if we're given measurements with finite ranges, we're not going to be able to cover the infinite range with finitely managed measurement. And this is a compactness at a topological level, basically. That's what it boils down to. And mathematically, this maps to property of open sets of topology. The topology, in fact, keeps track of the notion of closeness, and measurement resolution is about closeness. So the topology of a real line then is different from the topology of sets of points. The first one is topologically connected, while the second one is not. A space with a finite range is topologically compact, while one, there you go, I do say, while one that has an infinite range is not. Establish a perfect mathematical mapping between these concepts is not the goal of reverse physics, but rather physical mathematics. And I guess if I capitalize the P, I should capitalize the M. The point is, in classical mechanics, the mathematics characterizes and keeps track of these differences. The problem is, I don't know if I want to say the point is here. Maybe I should put this in a new paragraph. In classical mechanics, the mathematics characterizes and keeps track of these. The problem is that in quantum mechanics, the mathematical framework does not keep track of these differences. This is the problem we are going to explore in this section, a problem that is ultimately not solved, given that the mathematical framework does not capture all the elements and only the elements that are physically meaningful. The reverse physics program cannot be fully completed for quantum mechanics, so that we know that there are going to be problems. Okay, so any questions on this? I hope it's clear. I can wait a couple of seconds to see if any questions or anything comes up.
I can just say it makes sense to me, so.
Very good. At least it makes sense to one person.
Well, I hope two.
Yes, yes. Fair enough. Yes, yes, two. Let's say two. Okay, so now we can go with the part that we already discussed last time. I spent some time to write it, to rewrite it up, to make sure that things make sense. And this is the equivalence of Hilbert spaces. One feature of Hilbert spaces is that the cardinality of the base fully characterizes the space. In fact, let H1 and H2 be two Hilbert spaces. Would be two Hilberts. And let EI and GI be two orthonormal bases of the respective spaces with the same cardinality. Then we can define a map. Okay, so let's be two Hilbert spaces. Let's put with the same cardinality there, I think. It's amazing how many times you reread the same things and you always find problems. Two Hilbert spaces with the same cardinality. And let E1 and G1 be two orthonormal bases of respective spaces. Then we can define a map M from H1 to H2 such that the linear combination of EI becomes a linear combination of GI with the same coefficients. The map is unitary since if we make the inner product here or we make the inner product here, we get the same thing. And we saw a few times ago that if you have the same inner product, then, there is a comment. It makes sense, though I'd like to know why infinity can't be 3. I meant the types of infinities beyond particle council length scales. Like you mean infinities at a higher Aleph number, like infinities past continuum? I do have it here, if that's the question. So I'll continue, and then there is still an awful delay with the chat. So I'll keep going and keep an eye on the chat to see if that's what you meant. All spaces we're interested in quantum mechanics are going to have accountable bases. That's exactly here. If we imagine to extend to infinite the range of discrete observables, we can see that we will have a countable set of possible outcomes and therefore accountable bases. If we take the space of wave function in either a finite or infinite range, we will get the space of square integrable functions, which also has accountable bases. To see that, note that the Hamiltonian for the harmonic oscillator has a discrete spectra and therefore has countably many eigenstates which will form a basis. All wave functions then can be written as a superposition of eigenstates of the harmonic oscillator, and therefore the space has a countable basis. In quantum mechanics, then, if the space has infinite bases, it will be a countable one, which leads to the following observation: all infinite dimensional spaces in quantum mechanics are equivalent. If we have an infinite dimensional space, we're not going to be able to know whether we have a discrete quantity over an infinite range, a continuous quantity over a finite range, or a continuous quantity over a infinite range. Mathematically, there will be no difference in the states, unlike in classical mechanics. No, I'm here to get the comments. I'm not going to ignore the comments. I need the feedback. That's the point. So if people find something weird, they should tell me. Like that should be the point. We have to try to make this work online, and I don't know why, how. So I know why, because I need feedback. Okay, so let's continue. Okay, so that should be it. All countable things are the same. We made that point. And now we make the example. For example, the state space of a single degree of freedom, R square over of R, is going to be equivalent to the state space of n degree of freedom, R square of Rn. As we said before, the Hermite function, the eigenstates of a harmonic oscillator, provide a countable basis for a single degree of freedom. We can imagine a harmonic oscillator over 2 degrees of freedom. In that case, the product of the Hermite functions across degrees of freedom provide a countable basis for the space. And through diagonalization, we can map one set of the other. So we map 0 to 0, 0, 1 to 0, 1, 2 to 1, 1, 3 to 0, 2, and so on. And I put a comment here to add the picture of diagonalization so that to see visually what is going on. This idea can be generalized to map any sets of n degrees of freedom to any set of m degrees of freedom. Potentially, it means that we can construct a process that can encode the information of a billion particles into a single particle. Note that the above transformation is not possible in classical mechanics. 1 degree of freedom topologically is R2, while n degrees of freedom are R2n, which are not not topologically equivalent. The issue is that the topology of the Hilbert space in quantum mechanics is the one induced by the inner product and not the one induced by the observables, like in classical mechanics. Therefore, the mathematical representation in quantum mechanics knows too little about the physical system it is supposed to describe. And I think this is basically the only point that we want to get in this section. Then there are two other things that I started. We can do the discrete spectra. So I started working a little bit on the continuous spectra. For the domain of operators, I started writing a paragraph, and then I think during the session, we can go and get the paper that we wrote on the unsuitability of the Hilbert spaces for quantum mechanics, and there are a bunch of examples that we can take from there and stick inside here. So I think that could be an activity to do later. And I had started writing down something about the continuous spectra, so we can read that in the meantime. But first, did this part make sense? I think it's just what we discussed the other time. So Tobias nods, so we are in two people that think that this makes sense. Okay, so continuous spectra. In the finite dimensional case, we're used to associate possible values of unobservable to states, eigenstates, associating to that value. In the infinite dimensional case, this is where I put lots of S's everywhere. In the infinite dimensional case, we have operators that have a continuous spectra, like position or energy. I always want to have both of those examples. There is a temptation to extend the previous scheme to the continuous one, adding eigenstates of continuous values. And you can see that this wasn't reread because there are a lot of stupid mistakes. This is problematic, not just mathematically, but physically as well. Simply put, since we cannot prepare or measure a continuous quantity with infinite precision, these states are neither physically realizable nor measured. As we saw in the classical mechanics section, states as point in phase space, point particles, do not make sense in classical mechanics either. Volumes and areas define the geometry of phase space, as these define the count of configuration per degree of freedom and the count of states. And I will also add Hamiltonian mechanics is exactly the conservation of those areas and volumes. There we go. A single point having no volume can have no such notion. Classical point particles then should be understood as an infinitesimal region of space, a region so small that we do not care about its size, but still a region. In quantum mechanics, talking about particles at a point makes even less sense. If we shrink the spread over position to zero, we are forced to stretch the spread over momentum to infinity. A uniform distribution over an infinite range makes even less sense than a distribution concentrated at a point. Mathematically, a probability distribution over a single point is still a measure. A uniform probability distribution over an infinite range is not a measure. So this is something that, so I studied a lot of physics before studying a proper course on probability theory. And so, studying quantum mechanics, you get used to think about infinite distribution, this uniform distribution on infinite ranges, because that's how you are supposed to think about, position, eigenstates, and momentum eigenstates. And then the professor at some point said specifically that such a thing didn't make sense. And something clicked in my head and said, oh, there is a huge problem here. And so I do want to add it here, because I think it's important, because we are trying to define things that not only make no sense mathematically, but really physically, like it just doesn't make any sense. All right, so
can I ask one thing about this?
Yeah.
Because we can properly define a Dirac distribution, right?
Yes.
In a Schwartz space, so it's actually in a dual space.
Yes.
Right? But then the problem is that there is no corresponding state
Yes,
on the actual Schwartz space
correct.
because
So,
it's not self-dual. Um, I cannot, like, the Schwartz space and its dual are not isomorphic. I cannot map one-to-one from a Dirac delta onto a.
right.
Okay, I see.
So that also, you know what? At some point, I need to make a note. At some point, I have short space. So let's make a note to do a talk about the difference between Schwartz, Hilbert, and dual Schwartz dual, which is a space of distributions. So the way that it was that one guy put it that I talked to, and it was the thing that sort of made me understand the difference between these three things. So if you think about the Hilbert space as the space of accountable sequence of real numbers, right? That space is closed under like essentially any sequence whose sum is one is inside the Hilbert space. Okay, and so it can converge at any rate. The important thing that it converges. The space, the Schwartz space, instead, you are asking that it converges to zero faster than any polynomial, which means that not just the sum of all the PIs is one, so converges, but also all the sum of I to the n times PI converges. So you can multiply the sequence by any polynomial and you still something that converges, right? So it's going to go down faster than any polynomial because when you multiply by a polynomial, you get something. The space, the dual space, is the space of all the sequences that you can multiply to the sequences that converge to infinity faster than any polynomial and still have a number. Because the dual space is the space of any linear operator that you can apply to the Schwartz function. And any linear operator, you can understand it as multiplying each basis for a number and then summing it up. So you have a Schwartz sequence that goes down to zero faster than any polynomial. And then what you can multiply that and still have convergence is multiply into a sequence that diverges, but diverges slower than at some point some polynomial. And so now you have something that converges faster than the polynomial. You have something that diverges slower than some polynomial. You multiply, you have something that converges. And so the dual space, you can understand it as that. So you have the Hilbert space just converges. The Schwartz space converges faster than any polynomial, and the dual space diverges slower than some polynomial. And the delta function is going to be in the third space. So it's neither in the Hilbert space because it does not converge, and it's not, of course, in the Schwartz space.
So basically make the trade-off. My states are converging fast, but therefore I have more observables which can diverge,
Yeah.
but they need to cancel.
Yeah. And that's sort of how it works. And so I think the proper way to think about the dual is as the space of the observables and not the space of states.
Yeah, that's true. Also, in general, I was always confused by the fact that observables are now mapping states to states, but they kind of put like a weight on the state such that at the end I can take a trace or whatever and get something out of it.
Yeah.
But intuitively, why is it mapping states onto states? It would, I don't know. That's very different from what it does in classical physics,
Yeah,
right?
yeah, because and this is again another problem that I haven't. Well, that's a problem also in the class in the finite dimensional one. So the issue is that again we think about the Hilbert space as just a set of states, but if you think about it, when you're taking a state and multiplying it by a Hermitian operator, the Hermitian operator say that its position, right? It has a physical dimension, and so when I take the state, which you can think it as a probability distribution. So when I make the inner product of that state with itself, you get a probability. So the inner product, the norm of psi as a state is a probability. But if I now take the psi and multiply it by a position operator, and I take the norm, I do not get a probability. I get a position square. So the Hermitian operator does not map state to states, but it's going to map states to essentially the probability distribution multiplied by a position. And all of these things are completely not discussed, not treated, and it's a little bit like in classical mechanics, where you have one tangent space for everything. But clearly, if I have a vector that represents velocity and a vector that represents force and a vector that represents acceleration, I can't sum those things. And so they are not really mathematically in the same linear space. But again, since we are relying too much on the math, and the math does not have units or anything, you just put everything inside, but then physically you don't know what you're talking about. So yeah, it's a it's a bit of a mess, and trying to tease out all these pieces is yeah. So right now we are only worrying about the states. And you're right, at some point, we need to worry about these other things on the operators, but I think we can do those in the finite dimensional case, because you're going to have the same problem with the finite dimensional case. I have a spin operator, and I'm on a block sphere. When I apply my spin operator on my vector, the result has dimensions of spin. So clearly that's not in the same space.
So if I wanted to restrict myself to a Schwartz space, then my states would be density operators. Would they still be linear maps from Schwartz space to Schwartz space?
Yes.
From dual to dual?
No,
Or something else?
it should be from Schwartz space to Schwartz space.
Okay.
Because you can think, so when you're going to create the density operators over Schwartz spaces, you should be able to, every pure state should be a density operator. And so that's going to be something that takes a Schwartz space, a Schwartz function, and give you a Schwartz function. And let's see if there is other better argument than that. Right, because what you're going to be able to do is you can always you're always going to be able to diagonalize those operators. Even in the infinite dimensional case, you are going to need, you see, yeah, so even in infinite case, this is going to be interesting. I don't know if this is a good question. I probably have to write it down here. Okay, so does it make physical sense to have a mixed state over Schwartz, where the probability coefficients converge as a polynomial. That's an interesting question. So let me discuss it a little bit. So if I have a Schwartz space, I'm limiting myself to superpositions that go down faster than any polynomial. Okay, so that sum, that linear combination is about superposition. So things that take pure states and give you another pure state. Now, when I'm making a mixture that I take, let's say, infinitely many Schwartz functions, and I take the density operators corresponding to them, and I do the sum of pi, where that pi now is really a statistical probability. I'm creating an ensemble. So those probabilities are not superpositions, they're really mixtures. Now the question is, can I have things? What is the requirement on the convergence inside the space of mixtures? Is it the same requirements that I have in the space of superposition, or is it a different requirement? That actually I've never thought about it.
So you have lots of coefficients, you make like a huge mixture, and you have infinitely many coefficients.
Yeah.
And these probabilities, they converge in some sense.
Oh, they have to converge because the sum of all probability has to be 1.
There should be 1, yes.
Yeah. And I think it might still be a question whether, for example, if the original requirement is we want to have all the expectation of all the polynomial positional momentum to be finite, there might be something about that as well, but I don't know how it plays out. Interesting.
And is there, I need some kind of notion of order, right? For these probabilities to have something like a sequence.
Yeah.
But that shouldn't really matter, right?
Oh, the order does matter.
But what does it tell me, and the order in which I mix them, my states?
No, it's the order of the state. So if you think about it, right, even before we said we need to converge faster than any polynomial, right? That implies an order on the bases. Because if you do an infinite reorder, you can change the degree of the convergence. Right? You could stick, let's say, zeros, for example, in the middle, and then make the thing converge slower and slower and slower. And there is a sense which I haven't fully defined, like fully understood, that the ordering is important. And I think it's the same thing when let's say that you want to define, again, your countable basis of the topology on an infinite line, right? And your countable bases are going to be countable intervals, right? And so you're going to make intervals that go farther from 0, and they become smaller and smaller. I think there is a sense where, the one that go, farther from 0 and become smaller and smaller, right? How can I say? They become harder in some way. They become less and less where you are. So there is a sense in which you're putting at infinity the things that because again, we're really not going to have infinity, right? The infinity is just at some point we're not going to care. At some point we're going to make a cutoff. And then what we're going to want to do that when we made the cutoff, we have a set of nice things, essentially. And it could be that that's exactly where this ordering come from, is that when you're defining the ordering, you are implicitly, in a way that, again, I don't fully understand, but you're defining something that say, okay, these are the important things, and at some point I'm not going to care, and that's, that's how I make the cutoff.
Okay, so basically, if I understand correctly, the idea would be the order tells me where I can consistently make a cutoff because I say I don't have precision to distinguish these states. So this state, I throw it out. And then the order tells me all the ones above that state should also be discarded.
Yeah.
Okay, that makes sense.
And I think then the convergence, that it's faster than any polynomial, you're basically saying that most of the stuff that you're interested in is it's certainly, like, at some point it's localizable. Like if you have something that converges faster than a polynomial, then it's like the cutoff becomes more problematic. Like if I have something that goes down like an exponential and then I do a cutoff, it's clear that at some point I'm gonna say, yeah, I have 99% of my stuff within that interval. I'm good. While if it converges slower, it's doing that cutoff. I think it becomes more problematic because you're leaving a more significant part. Wow, yeah. Yeah, so all this stuff, it's kind of amazingly that I still don't understand. But now that I think about it, it kind of makes sense. If you understand infinity as something where you do a cutoff, the fact that you go down faster than any polynomial is essentially what allows you to say, oh yeah, I can make the cutoff. Because it's like you could be finite, that at some point you really stop, and then you don't care. And then you don't even have convergence over infinite things. But then if you have convergence over infinite things, you do want to say, well, at some point, I'm not going to care. And then at some point, I'm going to care. You basically say, yes, I have something where the distribution drops down so fast that that's why I don't care. And that surprisingly enough corresponds to the fact that all the polynomials of the expectation of all the polynomials is finite. This is interesting because now we have multiple ways um, of specifying the same requirements.
You were away for just a second, but everything is fine now. Anyway, do you think that's related somewhat to coarse graining? Could I phrase that as a coarse graining, cutting off?
So I don't like the word coarse graining because it has been used to do things that don't make much sense to me physically. If we back or crazy, if coarse graining, you just means oh, right, because now you're thinking of the cutoff of the infinitesimal instead of the cutoff of the range, right? Is that's what you're thinking?
Yes.
Yeah. So there, I have no idea because so that would be a different issue because the coarse graining so the cutoff at the precision depends on I guess on how fast things are moving, like how fast things are changing. It's like if you have higher frequency, it's like it's going to be a frequency thing in that case.
Yeah, probably something like a basis of Fourier modes would be more natural then.
Yeah.
Or maybe the order of my polynomial, because I don't know, higher order polynomials probably have more structure in some sense. I don't know. But
so if that coarse graining corresponds to wave modes, that could actually, like, we might be able to do some things with that. I never thought about it. I mean, at a signal processing type of thing, that's exactly how it happens. Like you're essentially discretizing, and when you're discretizing, you have the what is it, Nyquist theorem, whatever it is, like that you start have the aliasing between the faster frequencies and the slower frequencies. You can't tell them apart anymore. But I never liked that because I don't really want to do discretization. I don't think that works because like if we cut the precision, it should be still be something like that you can make translation. It's like if you cut off the precision, doesn't mean that you have cut off the precision where you can put the intervals. You haven't made the step of the intervals discrete. And so I never quite thought, what does it mean? So in principle, it's like you should be able to say, okay, I have a real line, I have a distribution of the real line, and the only thing that I can measure are like integrals over finite ranges, right? I think that's more information than, oh, I just cut off. It might even be enough information to actually recover the full function.
Wait, if I can measure any finite interval,
No, a
something
finite
like
region
that.
of a specific size.
Yes, I fix the size, but I can slide my interval to any place.
Yeah,
That should, I can just take two intervals and then make them arbitrarily, like I can measure the overlap of any two. So I still can measure anything I want.
exactly.
No, I would, coarse graining is probably something more like a convolution with some kernel or something.
Aha.
Probably. And then the higher modes will be basically washed out in some way. But at least the order in which we use Fourier modes like naturally maps onto how we coarse grain because we put the higher modes at the end.
Yeah,
That's the order we use, and those are the ones that are washed out by coarse graining.
yeah.
So, and if we would mess around with the order, um, probably we get problems. And so if we want to consistently coarse grain, I'm just thinking that the coarse graining could tell us what the order should be.
Yeah. No, I think you're right.
And it
Okay,
makes
so
sense
if you
for
if
Fourier
you
mode.
think it like that, then what you're saying is I do a Fourier transform, and then you're repeating the same argument on the infinite range on the range in frequency. Like the same argument that we made in position, you would do over essentially
I
momentum.
restrict the range, but in the momentum domain, in
In,
the
in the frequency domain, yeah, it's
yes,
in
yes.
classical mechanics is not going to be momentum. It's going to, yeah, in
True.
the frequency domain.
Actually, yes. By the Fourier transform, they become the same argument, yes.
Huh. Okay, I didn't think about this at all. Okay. Yeah, so if there would be a way to define coarse graining like that in terms of Fourier transform modes and so on, it might even be a very natural way to make the whole wave particle duality come out. Interesting. Yeah, I don't have a good intuition right now. I never thought about these things carefully.
And one detail is the a Hamel basis on a vector space. It's just a set of linearly independent vectors. A Schauder basis then really has an order, right? It's a list, not a set. Is that true?
You know what? I've never thought about it like that.
But I mean, we need one somehow, I guess.
Yeah, we do need the order. I do not know if the standard bases have a notion of order. Again, I never thought about this.
Okay, I just looked it up. It's
Yeah,
a sequence. It's not a set.
which one?
the Schauder basis is really a sequence of vectors and not a set of vectors.
Okay, interesting. So is it because
I
why
need to
why
know
do
how
they
to take the
define it?
limit, right?
Eh?
I allow limits of linear combinations. I need to know the order of my sequence of.
Well, that's the point. If I am in a Hilbert space, I don't need I don't need the order. It doesn't matter because any reordering is fine. Like if I am in a Schwartz space and I want to define a base, since I then define the convergence, then I have to give you an order.
So that's a special feature of a Hilbert space that the order does not matter.
Correct. It's a special feature of the
Okay,
Hilbert
that
space.
makes sense.
But it's because how you define the convergence. So if you have, let's say, the Schwartz space, typically, well, Schwartz space is particular because I can define the order in terms of the convergence in terms of order, but I like another way to define the convergence is with the topology, right? So okay, let's get a Frechet space. The Frechet space have the topology that it's induced by a countable number of semi-norms. So for any two vectors, you have a norm that tells you a number, and then you can make open balls with these norms, and you have countably many. And so as long as all your semi-norms converge, so if you have a sequence of vectors, you're going to have a sequence of all the values of those semi-norms. So if all the semi-norms converge, then your sequence of vectors converge as well, right? And so now you're defining a convergence that has nothing to do with the convergence of the coefficient. Like it doesn't matter. So even in that case, I don't know whether you would care about the order of the base because you're not looking at the order of the base for the convergence. So I'm surprised that it really says that it's a sequence, but also a sequence usually is countable. So does that mean that that thing only makes sense if you have a countable space?
Yes. So a Schauder basis, I think, only makes sense for a countable basis. I mean, you define, if it would not be countable, how do you define linear combinations then? You define them as a sequence, right? As a limit of a sequence. If you would have more than countable, you would need some kind of integral over all your basis vectors. That's again a different notion, right? So Schauder basis really only works for countable, I think.
Okay, so again, the Schauder is the one that comes with the inner product, right?
The Schauder basis is one where you just have a sequence of states and then you can take limits of linear combinations and you will include those. But
Right, but okay, so okay, so let's review the terminology. Okay, so there are bases that care about the inner product structure and bases that do not care about the inner product structure. So I can have a base that is just I'm allowed to make only finite combination, and that's the Hamel basis, right?
yes,
Okay,
the other one needs a topology which comes from a norm, which comes from the inner product. Yes, that's a Schauder basis.
okay. Well, does it need the norm, but it doesn't need the inner product?
It only needs a topology to define how to take limits of linear combinations.
Okay. And then there is the third one, which is the one that it's that requires the inner product, and so you're making an orthonormal basis.
I mean, if you want it to be orthonormal, yes, you can. You of course need to know what the inner product
Yeah,
is.
but I thought that
But
creating a basis using the using the inner product is different than creating a basis without it. And I might be confused, but I thought that the way that you define it is different and you get two different things.
I don't know which third type of basis you are thinking about.
Let me see. And then we are, showing my ignorance, orthonormal basis, which in Wikipedia just call orthonormal basis. And then there is the Hamel basis. Is not okay. The orthonormal basis in general is not a Hamel basis, and then that's fine. And then the Schauder basis, it has a different article. Okay, so that doesn't tell me much. Okay. Okay, so I think we're saying that an orthonormal basis is a Schauder basis, but not all Schauder bases are orthonormal, right?
I think you can, if you have a countable basis, either Schauder or Hamel, there is this process, Gram-Schmidt process, that makes it
Yeah.
orthonormal.
Okay.
I think that would work with both.
Okay. Now we were saying instead, if the space is let's see, does it say anything about countable? There you go. Notes that some author defined the Schauder basis to be countable, while others use the terms to include uncountable bases. There you go. So you could have an uncountable base, but then all the linear combination are overcountable.
So you would have even more states, but for each vector, you only use a countable subset, and then you still need to take limits. Maybe, yes.
Yeah.
But on the other hand, really, if you use a Fourier transform, this is also finding coefficients, and now it's continuous. Now I really integrate over continuously many Fourier modes, which I can think of as basis vectors.
And no, that's the problem. You can't do it because those would be in they are delta Diracs. So you're not integrating over a basis.
Yes, but maybe that's what people. Okay.
Yeah, that's what people
You
think,
want
and
to
that's
get
what I
even
was
more.
about to write. That it becomes problematic because so if you thought about Fourier modes, each mode as an element of a basis, you would have an uncountable base. And then is your space countable or uncountable at this point? Like it doesn't make any sense because the space is countable. You have a countable base, and then when you're defining the integral again, it's not a linear combination. It's something different, as you were saying.
Yes, I'm just saying whenever you want to extend this, you need some new notion of how to make linear combinations. It does not naturally generalize. The Hamel basis works in any dimension whatsoever.
Correct.
And basically you have by hand to come up with something for a countable, infinitely countable basis, and then maybe you can come up with some even more general stuff like a Fourier transform, and even, I don't know if you can make this consistent, but you would need a new notion of linear combination every time.
Yeah, so for what we need in quantum mechanics at the end of the day, you're just going to have a countable, the countable combination. And again, we're going to have two types of linear combination, one the superposition and one the mixture. And so the question that we have here now, we have added there is those probably are two different specifications. Because one represents the limits of sequences of pure states that want to give another pure state. while the other one represents limits of sequences of mixed states with the end result of being a mixed state. So in classical mechanics, you could imagine to make a limit where you have a sequences of point in phase space. You're making a limit and you get another point on phase space. And some of these are going to converge to a point in phase space, and some other instead they go to infinity and they don't converge. And then you could have sequences of probability distribution in phase space, right? So for example, you make a distribution that converges to a uniform distribution, right? That they become more complex and then it converges to a uniform distribution. That's good. Or you could make a series of Gaussian that become more and more pointed, and then they wouldn't converge in the space because the density would go to infinity. And so that stuff I already have thought about because I realized that these were two different problems because of the work that I'm doing on generalized ensemble spaces. I realized that there were these two different things, and I was thinking about them as the same thing, and then I couldn't get the math to work. And then once I realized that those two things were different, I could say, aha, now I actually, the math makes more sense, and I was able to actually fix some things and prove some theorems. And so here's going to be the same thing. I never thought about, so I still don't know what the rules of convergences are. I just know that there are two different rules. Okay, so we outlined all the points where we're still very confused and we need to, but I still think that there is no, like I've never seen these things discussed. I really, I don't know, a lot of people don't even have clear in their head that superposition is different than mixing the statistical mixture. So geez. Okay, so we go back to the text and see what I've written. And you had to go, Tobias, in some time, you said.
Yes, I have a different meeting.
Okay, very good. Okay, so let's continue and let's finish this.
Okay.
In quantum mechanics, talking about particles at a point makes even less sense if we shrink the spread. Okay, we were at, oh, they were not measured. Mathematical probability distribution over a single point is still a measure. Uniform probability distribution over an infinite range is not a measure. And one way to see this is that it does not satisfy countable additivity. We can imagine dividing the real line into countable intervals of equal size. Each should correspond to the same probability because it's uniform, and the sum of all contributions should be 1. If each interval corresponds to finite probability, then the sum is infinite. And if each interval corresponds to 0 probability, the sums correspond to 0 as well. And so the solution would be to sacrifice countable additivity so that each interval has 0 probability while the total is 1. Therefore, this would not satisfy the axiom of measure theory and would not and measure theory and probability theory. All right, so that doesn't work. And then, oh, maybe Tobias, maybe you know this. So you know that if you make the inner product between, oh, this should be equation. If you make the inner product between a delta Dirac and a function, you get the value of the function at 0.
Do you know that's technically not an inner product, right?
Yeah, sure.
You just evaluate the distribution, yes.
Right. So do you know, and this is, I want to be 100% sure, do you know what happens if psi is discontinuous? Or does anybody know what happens if
so on an L2 space, you only have equivalence classes of functions. They don't have well-defined function values, right? You don't know. That's why you restrict it only works on a Schwartz space where you have actual functions with actual values. And if you don't have that, you don't know what you're supposed to do.
Okay, that's exactly was my,
Yeah.
and you confirm this mathematically. That's exactly what happened.
Yeah. I mean, I don't know if there are other funny ways, but I mean, on an L2, it doesn't make sense. And in Schwartz space, you actually know what the function value is, and everything is fine.
Yeah,
That's good.
this is exactly what I was going to put.
Okay, yeah. Okay, now I really have to leave.
Bye.
Bye.
Question: the assumption as infinite in the real line is open and closed. Well, infinite open and closed are about sets. It's not about infinity. So infinity is the range. So I don't know what it means for infinity to be closed or open. Okay, so I think that's where we end on this section, because I still need to write everything. What I think I can do, I can work on this by taking the example that we already have developed that shows how you can get the energy to oscillate between a finite value and infinite value in finite time, and start sticking it there, because I think it's going to be useful. So let me get, I should have the paper somewhere here, right? Yes. And then this is, there you go. This is fun. And we can get this whole thing and review completely the text. Which is here. And here, let's do it. Okay, so for example, consider the following two-wave functions. Okay, so the cool thing about this example is that we're going to take a one-wave function that goes down like an exponential. So this is a Gaussian state. And a state instead where the wave function goes to 0 like a polynomial, like the inverse of x squared. And then we can find a function that maps one wave function to the other. And it's going to be the tangent of the error function. And so this is an invertible covariant transformation that that in principle one can do on wave functions, but it is going to map something that goes down to infinity faster than any polynomial, like a Schwartz function, to something that that does not go faster than a polynomial, like that it goes like 1 over x squared, and therefore you're going to take something like the expectation value of x squared will go from 0, well, we'll go through, I guess it's going to be 1 here. I should calculate that. And you're basically stretching something so much that the variance becomes infinite. And then again, that shows you that you can't just make any transformation that you want. You're going to introduce things that are problematic. Okay, so in Cantor's trans-infinity or infinity on infinity as category of slide, I don't understand what that means. And classes or types, I don't understand what that means. Okay, so let's get the following two-wave functions. Okay, but this is okay. note, and no, I should also put the probability distribution here to show that it's if we look at the probability distribution of the first, this is rho of x equals frac of 1 over square root of pi, and e to the minus x squared Did you get it? Oh, I must have done some mistake as usual. Undefined control sequence. What did I do? Why is it not compiling now? Wait a second, is there an issue there? How much I hate. So in the center, where is the line? Where, of course, I don't know the line because this is latex, so I'm not going to be able to know where the problem is. So why don't I do things like this? All right, so this compiled. And now it's probably this section. No, it's not that section. Okay, so the site is not going to be there, so let's remove that. Okay, where is the... This is going to drive me nuts, I already know. Okay, so if I remove all of this, it compiles. Very good. Okay, so now if I remove only this, it does not compile. So it's inside here. No. What is happening? Okay, so if I remove this whole thing again, and it's like if I remove everything, it works, but if I remove one section at a time, it doesn't. But then the overlap is what is the problem? Oh, it's gonna be this? No. Okay, I'm apologies, but I don't. Okay, so if I remove this, but if I remove this, it still does not compile. Okay, so there must be the same thing in both. Oh, this symbol of tan was defined in the article. Is that the issue? Let's see. Did I define tan as a symbol up? Oh, the error function I defined up. There you go. Oh man. Okay, so where can I declare this symbol now? Can I just declare it up here? Does that work? Ah, okay. I need to define it in the package, I think. Yes. Let's define it in the package then. Can I open it? Oh, man. Okay. Okay, where do I define the things? I don't have a nice section, so let's add one. Special functions. Okay, so now if I go back here, okay, so it had real. Okay. Okay. Axiom, I'm sorry, I still don't understand what is Galois, Abel algebraic approach. I really don't understand what you're talking about. And hello, memes of discretion. What's going on? I am adding a section about this example in which we have expectations that blow up to infinity and go back down. So, okay, so for example, consider the two-way function. I could introduce them one at a time. So for example, let's consider the follow wave function, and then we are going to put, so let's describe them one at a time. That probably is a little bit nicer. So this, and then rho of x, and let's put a psi there so that we remember that that's the psi, and this is going to be equal to a psi dagger side dagger x psi of x, and this is going to be equal to this. Okay. And let's see, I should, why don't I go and look at what the variance of this thing should be? Is it 1 or 1/2? Let's see, Gaussian distribution. And the distribution is, yes, there is a 2. So that would be, and why don't we put the 2 so that it's a little bit better. And so if I put, let's see, how do you usually have it? It's a minus x squared over 2. Okay, so minus, I'll put the frac here. Okay, so now this looks more like a Gaussian, and I also need, at this point, I would need the 2 here as well, right, in the square root. And now this would correspond to a Gaussian that has variance 1. Okay, good. It's a normal distribution. We're being so normal. And so now we put the 2 here, and then we are going to get this, no, where is it here? here, here. Okay. Let's see if it looks right. Okay, and at this point, I'll just write it in the standard way that it's written with the exponential outside. But this is inside the square root. And then this is a1. Okay, 1 over square root of 2 pi e to the x squared over 2. And so, okay, so consider the following wave function. This is a Gaussian wave packet with with 0 expectation and 1 variance. That sounds funny. With a 0 with expectation of 0 and variance of 1. Very good. Now consider the following wave function. And this is going to be the phi. And now this is going to be, again, a rho phi. And then phi dagger phi. And then this is just 1 over pi. Let's remove this. No need for this. And this is just 1 over pi. X squared plus 1. I should also add plots for this thing. Let's put this to do add the plots for the wave functions. That would be useful. Okay, so these have disappeared. What did I do? Of course, there are multiple problems, and what are they? Okay, phi equals square root of that. That I didn't change. Except so if I just do this, what happens? Okay, so why if I add something, suddenly nothing works? Fantastic. Okay, so this is rho of phi of x equal phi to the dagger of x. Phi of x equal the fraction of 1 over pi x to, this extra thing. Okay, we got that. Okay, so now I have to remember, so the expectation of this is 0. Since okay, so note that this, that's 5. Goes to 0 as 1 over x squared. The expectation then will converge and will converge to 0 since the distribution is symmetric. However, the variance will diverge since limit of the limit limits for x that goes to infinity, of x squared times this thing. So, oops, why didn't it go down? Oh, oops, like this. There we go. So that thing should go to, let's see, to 1 over pi, right? Hopefully it's 1 over pi. Frac 1 over pi. Right? The limit is x squared. So as this thing goes to infinity, this goes like x squared, this goes like x squared. They simplify, and I get a pi down. So it goes like 1 over pi. And so the thing is going to not converge. Okay, now in the Hilbert space, so these correspond, these both correspond, correspond to two vectors. Both of these will correspond to two vectors in the Hilbert space, meaning we are going to be able to find a unitary transformation that moves, that changes one to the other. In this case, we can do that by a change of variable. That is, we are going to look for a transformation y equals y of x that transform one wave function into the other. We what we require is that the integral of one function over one region equals the integral of the second function on the second region. And again, this would work a lot better with a picture. But mathematically, what we're going to do is this is the row of phi. So this is the density, the probability distribution over y. This is the density distribution over x. And we want that this integral between 0 and x is going to be equal to the integral of this from 0 to y. So, now we have the integral variable being y hat, so that then y becomes the range of the integral. And the same thing here, we have x hat as the integration variable, and x is the actual integral, the boundary. And we're going to have the relationship that this boundary corresponds to the transformed boundary on the other side. Now we put these, which if I need to change them now because I put a factor of 2 so that I actually have a normal distribution. And so let's go do it by using this. And this is the function. There you go, which we can now stick inside here before the dx hat and inside the integral. There we go. Okay, so now we are saying this integral is going to be equal to this integral. And now, okay, this is going to be the error function without the over 2. Right? Because the error function is precisely the integral of the normal distribution. Let's double check that. Normal distribution. Let's see. Do I know erf? Okay, so the error function is gives a probability of random value with normal distribution of mean 0 and variance 1/2. Oh, so I should have kept the 1/2. Oh man. Because the factor of 2 came from the fact that I'm doing the integral from 0 instead of minus x. Okay, so. Oh man, I don't want to screw this up. So. Okay, well. You know what? No, I should just do it. Let's see. Let's see. No, I'm not gonna be able to do this here. Oh man. All right, so now I need to double check what is the integral of a Gaussian normal distribution, like a normal distribution. So let's see. So the error function is I need to make a change of variable, therefore that's gonna get a coefficient somewhere. Community distribution function of the standard. I don't want the cumulative distribution function. Oh, well, wait a second. Okay, there it is. It's right. It's gonna be 1/2 right. Okay, so what I want, this thing, it's gonna be the cumulative distribution function of the normal distribution minus 1/2. Because the cumulative distribution function is the integral from minus infinity to x. And its distribution function is that. And then I want to go from 0, and the integral of the Gaussian from 0 to minus infinity, or the normal distribution from 0 to minus infinity is 1/2. So it's going to be that. So it's going to be a 1/2 the error function of x over square root of 2. That's what I'm looking at. So it's still 1/2 here, but the x has to be f x. Okay, so that's why I had the variance of 1/2. I'm tempted to actually just go back because this looks nicer if there is no square root inside. Fine. Okay, let's I had a reason to do the things that I did. Okay, so remove this and remove this. I should have looked all the way. Okay, so this now is this, and this is just the Gaussian zero and variance 1/2. Okay, so now the variance is 1/2, and so it's going to just look nicer here. And so we remove what I did here. It's not the 2 anymore. Okay. And now this is indeed 1/2 the error function, because the error function would be the integral of this from x to minus x. And since we're going to do it from 0, and since it's symmetric over 0, we get 1/2 of the error function. And this we, of course, chose such that we could integrate it easily. And the integral of 1 over 1 plus y squared is going to be the tangent, the arctangent. And so now we have the arctangent here over pi. We have the error function, and we just invert it so that we have the tangent. And now we have this wonderful function. Y of x is equal to the tangent of pi over 1/2 of the error function. Okay, so we can change from this wave packet to this wave packet with just a change of variable, and a change of variable is a unitary transformation. Okay. Okay. Since this change of the variable then changes, maps a state with finite expectation of x square of position square to a state with infinite expectation. The changes of variable are unitary transformation on the Hilbert space. So we have found that and so, okay, change the variable, the unitary transformation on the interface. So in general, a unitary transformation can map a finite expectations to infinite expectations. Okay, so this I don't need. Okay, so this language, I don't think I need it. Okay, to be clear, the position in each reference, the position in each reference frame corresponds to different observables, that is x and y are going to map to two different Hermitian operators. However, if we wanted to want the principle of relativity to hold, Um, chip. Um, I don't know how to express it right now, so I'll just put to do finish the paragraph. As it's starting to get late, so I don't think I am going to do much else. Okay. Now that we okay, so we can also map one moreover in a Hilbert space we can always map one vector to another vector through a continuous unitary transformation through continuous evolution. That is, we can construct a time evolution operator that maps, okay, so mathematically, we can always rotate one vector on top of another. Physically, this means that we can construct a time evolution operator that oscillates between the two states. For example, we can write, and this is a nice thing, so we can write something where the variable changes in time by going from x to the tangent of pi error function x. So we basically have something that transforms the variables, right, continuously, and then allows you to go back and forth. But since we have this cosine and sine omega t, we keep going from one coordinate to the other coordinate, right? And this is a time transformation. This is clearly continuous in t and this is, okay. So, for example, we can write this is a continuous transformation in t for t equals 0. This is just the identity as I'd rather say, instead of z, that, why there is a z. So why don't we just say x of t, and then here we just put x0, and then x0. There we go. We can write a for example, suppose the evolution is such that the position changes in the following way. This is a continuous transformation in t. For t equals 0, we get the identity as x of 0 equals x0. then we say at for t equals, let's see if I get this correct, for p equal pi half, frac pi half, we get x0 equals the tangent of OS or if psi of x is the initial state, we will have psi of x we have the cases, the evolution will oscillate between the two states, transforming a finite expectation to infinite expectation and vice versa in finite time over and over. There we go. That's what Hilbert spaces allows us to do, to make things that not make physical sense. Okay, so since it's been already an hour and 40 minutes, I think I'm going to stop. And if there are questions of any nature, I'm happy to stay here discussing things for another 20 minutes. Otherwise, we can close it. So I'll wait to see if there are questions from the chat. And in the meantime, maybe I can commit to GitHub and push. And mechanics. I don't see any questions. Let's give it another 30 seconds, but I don't think there are going to be questions. WWKK, yes, I think if we get a physics that is always intuitive, where the math always maps to things that are reasonable physicals, we are gonna solve, like, a lot of the things that we think are problematic right now are just gonna disappear. Like there is one thing that I have found is that the mathematics that it's nice and useful to do calculation is not necessarily the mathematics that allows you to see the physical the physical concepts in the most straightforward way. And in quantum mechanics, this is even more true. And so one of the things that I've been trying to do in some other work is trying to find a starting point where things are much better, and where both classical mechanics and quantum mechanics can sort of be seen at the same level, in the sense that you have physical theories that gives you yes, the formalist gets in the way of the intuition. Yeah, it's Yes. So Hilbert spaces are nice computationally because you have the linearity. It allows you to do many things mathematically that are nice, and even the completeness. This idea that you can get all the limits. It's a nice mathematical property that allows you to prove theorems and to make calculations, but it's not. It's not a physical requirement. And so if you take it literally and you say, okay, the space of states allows you to make all these limits, and then you have all these expectation of things that are infinite, and you're restricting a mathematical space, that then it's hard to understand what is physical and what is not physical, because everything is jumbled up. And I think this has been the sort of the problem with in the last 100 years, where the mathematics has took a route to make things more abstract because it's useful for mathematics. And physics, instead of saying, okay, what is it that we need at the foundation? What are the mathematical abstractions that make sense for physics? They just took what math did, including things that don't make sense in physics. In the previous discussion that I was having with Tobias, there is this idea that a Hermitian operator takes essentially a probability state, and what gives you out is something that has to have the physical dimensions of the quantity that it's describing, and the math does not take that into account, and we put everything together, and then we don't understand what's going on. Right, and I do think renumerization and all of those things are going to be are going to be some mathematical representation of something where you're taking maybe something that physically is not even relevant, and it becomes so you take something physical, you make the mathematical space, and to make the mathematical space you you add the things that don't exist, and then you have to sort of keep getting rid of them because they don't represent the physics. And I think that renumerization might be one of those things, as though I am staying away right now from field theories because I don't know how to do quantum mechanics properly with everything nice and clean, and classical field theory with everything property and nice and clean. And until I can't do both, I'm not gonna even try to attempt quantum field theory. I think it's just gonna make the problem compound, and then I don't understand anything of what's going on. Yeah, and I do think that a lot of things that people are trying to do in the foundation of physics, beyond the standard model and Planck scale physics, I really do believe that it's like you need to figure out the simple things first before doing these other things. And maybe once you fix all the all these hairy issues, maybe the other questions get solved by themselves. I really respect your procedure express. Thank you. Okay, here's the thing that I find I don't know, confusing, is that it's very hard to do this approach in standard academia. Like I have problems finding journals and finding reviewers for this type of work. And I kind of, in some level, I find more support on people like you on YouTube, or people that I meet through social media. And I don't understand. Yes, we have to start with strong foundation, and you can't do that later. I don't understand why this is not done. Well, part of it is the funding, part of it is the culture, but yeah, I don't understand why this is not done, and that's kind of why I'm doing it, because I don't see. It's interesting because there are people in the math that do try to do things rigorously at the math level, but they don't have the physical intuition, And so I don't think they go most of the time in the right direction. And the people that have the physics intuition that works on the physics, they sort of disregard the math as a mathematical detail, and then they go to other problems. And yeah. Yeah. So anyway, so that's kind of why I'm doing this on YouTube, to try to find, because I know that there are some other people like me scattered, that maybe they're still connected in academia, and then maybe they're still doing some more, or maybe they actually would like to do this type of things, but uh, again, you have to find people to do them, because if you are just by yourself, you're not going to find journals and so on. So my hope is that by doing things in a very public way, we can find a critical mass and start doing things. Yeah. Any other questions? Hmm. Right. We'll stop it here then. Thank you to everybody. Thank you for, and I'll see you next time. So next time, I think I'll try to do this idea of going through open problems, because that might be more useful for people that watch the video, not in the live, and then maybe have some idea on how to help, and then they can leave me comments. Last time there was a very helpful comment on what is it, Kronecker product and stuff. So this is kind of like the things that I like to get most. Anyway. See you next time. Have a good weekend.